Hello and welcome to this quick take video on getting started with Vivado high-level synthesis. In this short video, we'll first review the files associated with an example design project and then use this design to highlight the features of Vivado HLS. We'll show how Vivado HLS can be used to easily create a new synthesis project, validate the function of the C design, and synthesize the C design to an RTL implementation. We'll then complete this video by demonstrating the Vivado HLS Tickle interface, showing how the initial GUI-based project can be used as a template. The design example used in this video is a simple fir filter. This filter is implemented with the following files. The function to be synthesized is called fir and is captured in file fir.c. The file fir_test.c is used to confirm the fir function operates correctly and is considered to be the C test bench by Vivado HLS. The test bench reads data from file out.goal.dat. Both C files refer to the header file fir.h. Vivado HLS invokes showing the welcome screen. Here we can see the options for managing projects. We can create a new project, open an existing project by navigating to the project on the disk, or select from a list of recent projects. By selecting Browse Example, we could also open a project based on one of the examples provided with Vivado HLS. Finally, here on the left-hand side, we can access the Vivado HLS documentation and tutorials. For this example, we'll start by creating a new project. The new project wizard opens, and we can see that the first field in which to enter data is the project name. Here we'll enter the name fir_project. This will also be the name of the project directory on the disk. Next, we can specify where this project will be located. Since this is a C project, we'll leave the top level as C++. Pressing the next button allows us to specify the function to be synthesized and any associated files. The first field is to specify the top level function name. In this example, the function is called fir. Here we can add files which contain the C function to be synthesized. In this example, there is only a single file. However, if there are functions below the top level function and they are in different files, those files should be included here. Pressing next allows us to specify the test bench files. In this example, the test bench is called fir_test.c. Since this test bench reads data from the file out.goal.dat, this file must also be included in the project, and holding down the Shift key allows us to add this file to the selection. Pressing Next takes us to the final screen of the project wizard, which allows us to specify the technical details of the initial solution. We'll leave the first solution name as the default, solution 1. Here we can specify the clock frequency as 5 nanoseconds. The clock uncertainty is used to model delay due to place and route, which are unknown at this point in the design flow. The clock uncertainty is subtracted from the clock period to create an effective clock period for high-level synthesis. Vivado HLS will create a design in which there are no logic paths which exceed the effective clock period. If we leave this blank, it will default to 12.5% of the clock period. Next, we can select the device. For this example, we'll simply select the first Artix device. Pressing Finish opens our new Vivado HLS project. The Vivado HLS Graphical User Interface, or GUI, consists of 4 panes. We'll discuss these in turn. The Project Explorer pane, the Console pane, the Information pane, and the Auxiliary pane. We'll explain these as we start to use them. We can begin with the Project Explorer pane. Here we'll see the objects which are associated with this project. Here we have the source code. We also have the test bench files and the initial solution, which at this point only contains some constraint files. We'll discuss these later. If we double click on the source code, it will open in the information pane. Here we could edit this file to make changes and resave the file. Notice, as soon as we open something in the information pane, the auxiliary pane opens to provide more information. Since this is a C source file, the outline tab shows some of the objects in this file. Behind that, the directives pane shows which objects in this file can be optimized. Here we can see any function in the source file. Since this is the top level function, we can see the top level arguments. These will be synthesized into I/O ports. Any arrays which are in the design file, and any loops. If we select and right click on any of these objects, for example the loop, we can specify an optimization directive. For example, we could specify that the logic in this loop is to be pipelined in the RTL design. For now, we'll forgo any optimizations. All the steps to synthesize the design are available in the menus, and they are also provided for easy access in the toolbar. The steps are ordered left to right. We'll cover each of these steps in turn. The first step, which should always be performed in any project, is to validate the C design has the correct functionality. In other words, let's simulate the C code. The build button will compile the C code. Here we can see the output from the compilation is written to the console pane. If the code compiles successfully, we can proceed to run the design. And here we have two options. We can run the code in the debugger, or we can simply run the code. The debugger is discussed in more detail in the quick take video verifying your Vivado HLS design, and so for now we'll simply run the code. The C simulation completes, showing the results are correct. Now that we've validated the C function and confirmed it is indeed correct, we can proceed to synthesis. Pressing the synthesis toolbar button starts the synthesis process. When synthesis completes, the report for the top level function opens automatically in the information pane. Notice over here in the Explorer pane, the solution folder now contains a syn folder where the results of synthesis are stored. Within this folder are the reports and the RTL files in Verilog, VHDL and System-C. Since the information pane is now showing a report file, the auxiliary pane shows an outline of the report. Here we can select to review the performance, where we can see the estimated maximum clock frequency and the design latency, or the number of clock cycles it takes to create the output. We can also review the area. Here we can see the number of BRAMs, DSP48s, flip-flops and LUTs that will be used in the RTL design. The final step in completing the design process are the steps verify the RTL and export the RTL as IP. These steps are covered in detail in other quick take videos, and you're encouraged to review those for more details on these important steps. The final item we wish to cover in this quick take video is the Vivado HLS Tickle interface. In the solution folder, we can see that there are two constraint files. If we open the script.tickle file, we can see it contains all the tickle commands required to synthesize the design. Notice this file references the directives.tickle file. Since there are no optimization directives in this design, the directives.tickle file is empty. The script.tickle file can be used as a template to create your own tickle script batch file. To use the tickle interface, invoke the Vivado HLS command prompt from the start menu. On Linux systems, simply open a shell. After we've changed to the working directory, we can copy the script.tickle file to create a new tickle batch file. If we open this run_hls.tickle file in an editor, we can begin to change this. First, let's store the new results in a new solution, solution 2. Secondly, we'll change the target technology to a Vertex 7 device. The directives file in solution 1 is empty, but in general we do not want to use directives from another solution, so let's delete this. Now simply save the results. First, if we type Vivado HLS -help, we can see all the options for using the Vivado HLS command line. We can use the -f option to execute the Vivado HLS in batch mode with a tickle file that we have just created. When this completes, we can navigate into the directory to read the reports, or we can open this in the Vivado HLS graphical user interface. Using the -p option with the project name will invoke the Vivado HLS GUI. In the Explorer pane, we can now see the project has two solutions. This completes the Getting Started with Vivado high-level synthesis video, and thank you for your time.